Hello, and welcome to our presentation for PBHL 6110 Applied Linear Models. My name is Indy, and we also have Irla here, and today we'll be discussing the impact of BMI and prenatal care utilization in relation to pregnancy health variables. So what is our question? Our question is, how does prenatal care utilization affect BMI of the mother? And does this relationship differ amongst various maternal age groups? Taken from the 2018 natality data set, the methods that we have taken includes demographics for health information such as age, race, sex, birth weight, gestation, prenatal care, and more. The National Center for Health Statistics collection data on birth through the National Vital Statistics System natality, which is where this was derived. Also, derived from the NVSS the NVSSN obtains information from registration offices in all 50 states, New York City, the District of Columbia, and U.S. territories. The sample size that we have used was 3 million births used in the data set, but for this proposal specifically, we are using 100,000 births. And that would be our data points as well, 100,000 births. And so here are our variables. Looking at the dependent, we have BMI of the mother before pregnancy. And looking at our variables here, we have our independent variables, such as maternal age, measured continuously in years, representing the age of the mother at the time of delivery. We have prenatal care, quantified by the number of prenatal visits during pregnancy. And last but not least, we have health variables used, such as gestational hypertension, diabetes, and preeclampsia, all being categorical data. So what are some of our defining characteristics we have here? And we have a higher risk of pregnancy can be directly associated with gestational age at which the infant is born. Another characteristic is a mother with higher BMI can be linked to the frequency of prenatal visits attended during pregnancy. So what are some of our defining characteristics, descriptive characteristics? So we have here where BMI's values are tightly clustered around the mean, indicating less variability. With the standard deviation for BMI being small, that means 97% of the data lies within two standard deviations of the mean, 1.352 and 1.386. Here, if we look at the table to the left, we can also just look at other descriptive statistics we have for log BMI, mother's age, prenatal visits, and hypertension, eclampsia. Our means for log BMI being 1.4228, mother single age, 3.3482, prenatal care visits, 2.3738, and hypertension, eclampsia being 0.6915. And also in the table, we also have the standard deviation and our sample size. Looking at our pairwise plot. In this plot, the residuals appear to be fairly scattered and evenly spread for most predicted values, but show some variation at higher predicted values. This could indicate slight heteroscedasticity, where the variance of the residuals is not completely constant across the range. Here we can see in the scatter plot for log BMI, we have, obviously in our Y, we have our regression standard residual, and in our X, we have the regression standardized predicted value. You can see a very hefty cluster of data right smack in the middle between negative 5.0 and positive 2.5. And then we have a few unclustered data, less scattered around less clustered data from around 5.0 to 7.5. Let's look at our scatter plot graph as well. Based on this visual scatter plot graph, there is no correlation between the two variables plotted, log BMI versus mother's race. The vertical lines means that within a mother's racial category limited, there is a wide range of BMI values, suggesting that there's no trend across the data. This indicates that race alone is not a significant predictor of BMI. This information was utilized in our previous data within each racial category. We have come to learn that race is not a significant factor in predicting BMI. Other variables, such as hypertension, eclampsia, age, and prenatal visits, might play a significant role in influencing BMI during pregnancy. So race was not used in our most recent data findings. So our hypothesis testing, we have our null, which is there is no relationship between BMI and the predictors such as prenatal visits, mother's age, and hypertension, eclampsia. And then we have our alternate, meaning that there is a significant relationship between BMI and the predictors, prenatal visits, mother's age, hypertension, eclampsia. So what is our regression standard error and hypothesis test? Obviously, we have our hypothesis test. There is no relations between BMI and prenatal visits of the mother during birth. Then we also have our hypothesis test being that there is significant relation between BMI and prenatal visits. Here we have our table 3. Here we have our table 3 and table 4. And here, when we look at our model summary in table 3, R2 indicates a 0.3%, meaning R2 indicates a value of 0.3%, meaning that only 0.3% of the BMI of the mother can be determined by the number of prenatal visits the mother has during pregnancy. This also tells us that prenatal visits may not be a very strong predictor of BMI of the mother. Here we also have our histogram. This histogram shows a positive skew graph, suggesting most of the data points are concentrated on the left, indicating obviously our lower values. But there are very few outliers on the higher end that pull the distribution to the right. This could mean that the mean is usually greater than the median because the higher values, our outliers, raise the average. And next we have our QQ plot.
This slide represents a QQ plot, which is a graphical method for comparing two probability distributions by plotting their quantiles against each other. In this case, the QQ plot helps us determine whether the data follows a normal distribution. As we can see from the plot, there are significant deviations from the line, especially in both the lower and upper tails. The points in the lower tail on the left side fall below the expected line, which means the observed values are smaller than what we would expect under a normal distribution. In the upper tail, to the right, the data points are much larger than expected as we deviate significantly upwards from the line. What this tells us is that the data is not normally distributed, and these deviations could suggest the presence of outliers or indicate that the underlying distribution from our data is skewed. So overall, the QQ plot clearly shows that the data distribution is not normal, which should be kept in mind as we interpret further statistical analysis. Now we go to the multiple linear regression slide. Here we have the results of the model, and the goal of this analysis was to examine how the number of prenatal visits and a recoded version of the prenatal visits influence BMI. The R-squared value for this model is 0.003, which indicates that only 0.3% of the variance in BMI is explained by the independent variables. Looking at the coefficients, we see that the log P and V had a positive coefficient of 0.041, but the standardized beta coefficient is quite small, indicating a weak relationship. For the second variable, the number of prenatal visits recoded, we see a very small negative coefficient of minus 0.002, and this suggests that there's a minimal negative relationship. And again, the p-value is not significant, showing that there's no meaningful influence of having no prenatal visits on BMI in this data set. Although this model provides some insights, it points to the need for a broader investigation and other variables to better understand the full picture of how the BMI is influenced during pregnancy. And now we go to our model summary. And this summarizes the performance of our model, focusing on the correlation coefficient R and the R-squared value. The low R value indicates that there are likely many other factors influencing BMI that were not captured by this model. This could include lifestyle factors, diet, or even genetic influences that are not part of the analysis. And additionally, the adjusted R squared, which accounts for the number of predictors in the model, is also very low, further supporting the conclusion that this model does not fit the data well. Let's go to the residual statistics. This slide presents the residual statistics from our multiple linear regression model, and the residuals represent the differences between the observed and predicted values of BMI. The regression standard error is a crucial measure because it gives us an idea of how far on average the predicted values of BMI are from the actual values. It reflects the model's accuracy in predicting BMI. In this case, the standard of error is 0.12946, which means that the predicted values on average deviate from the actual values by approximately plus and minus 0.12946. The smaller the standard error would indicate that the model's predictions are closer to the actual data points. Overall, these residual statistics show that while the model provides some reasonable predictions, there's still room for improvement. And let's go to the regression standard residuals of BMI slide. And the residuals are the difference between the observed values and the values predicted by our model. As you can see, the shape of the histogram follows a bell-shaped normal distribution curve. Most of the residuals are clustered around 0, and they're symmetrically taper off in both directions. This is an important indication that the residuals are approximately normally distributed, which is a key assumption for many types of regression analysis. Next slide. The PP probability plot. And this slide represents this distribution a strong indication. Oh, I'm sorry. In this plot, most points closely follows the line, particularly in the central portion, indicating that the residuals are approximately normally distributed. And this suggests minor departures from normality in the extremes, which may be due to a few outliers or slightly skewness in the residuals. And now let's get to the model building slide. Oh, the linearity and homogeneity slide, sorry. This slide presents a scatter plot that helps assess two important assumptions in regression analysis. Both assumptions are necessary for ensuring the accuracy and reliability of a regression model. The scatter plot shows the residuals are randomly distributed without any clear pattern, suggesting that the assumption of the linearity is met. And the spread of the residuals in the scatter plot remains relatively even across the entire range of predicted values, with no visible funnel shape where the points would fan out. This indicates the assumptions of homoscedasticity is likely met, meaning the variance of the residuals is consistent. And let's go to the model building slide, which is this slide summarizes the steps we took to build our regression model, and it highlights the significant predictors of BMI based on the data. First, we used the scatter plot of standardized residuals versus predicted values to check for linearity and homoscedasticity, and it allowed us to confirm that the residuals were randomly distributed and that the variance remained constant across the predicted values. And looking at the results, we found that prenatal visits, mother's age, and the presence of hypertension, eclampsia were significant predictors of the BMI. Through the model building process, we confirmed that the important factors such as prenatal visits, mother's age, and hypertension, eclampsia played a significant roles in predicting BMI, and these findings will help guide further analysis, interpretation of how maternal health and behaviors impact BMI during pregnancy. And let's look at the results. The slide summarizes the key results of the regression analysis, including their overall model significance, R, squared value, and the role of each predictor in explaining the variance in BMI. The overall model was statistically significant. This means that the predictors in the model, prenatal visits, mother's age, and hypertension eclampsia, explain a significant amount of the variance in the BMI. The R-squared value is 0.162, indicating that approximately 16.2% of the variance in BMI are explained by the independent variables. And this means that these predictors account for a considerable portion of the variability in BMI. We have also have the adjusted R-squared value of 0.159. And this shows that the model continues to explain a good portion with variance after adjustments. And then for the results. And the regression slide. This slide represents the final regression equation that predicts the BMI based on the key variables, prenatal visits, mother's age, and the presence of hypertension eclampsia. This regression model provides a clear picture of how prenatal visits, age, and hypertension eclampsia contribute to the changes in BMI. And so the regression equation is as follows: BMI equals 1.369 plus 0.006 times the number of prenatal visits plus 0.022 times the mother's age minus 0.048 if the mother has hypertension eclampsia. And the intercept is 1.369, which represents the expected BMI for a mother who has no prenatal visits. And the prenatal visits, for each additional prenatal visit, BMI increases by 0.006 units, indicating a slight positive association. And for every additional year of age, the BMI increases by 0.022 unit, suggesting that older mothers tend to have a higher BMI. And if the mother has hypertension and eclampsia, her BMI is expected to be 0.048 units lower compared to the mothers without these conditions. And in conclusion, all predictors included in our model, prenatal visits, mother's age, and hypertension and eclampsia, are significantly associated with BMI, as demonstrated by their p-values being less than 0.001. The model explains a significant portion of the variation in BMI based on these independent variables. While there is still unexplained variance, the model provides valuable insights into how these factors interact and influence maternal BMI. And the relationship between these predictors and BMI is important for understanding maternal health. These variables highlight key maternal health factors that contribute to changes in BMI during pregnancy, such as the frequency of prenatal visits, maternal age, and the presence of hypertension eclampsia. And this information can guide further interventions aimed at improving maternal infant health outcomes by targeting prenatal care and managing maternal health conditions such as hypertension. Healthcare providers can help mitigate potential risks and promote healthier pregnancies. And that's it.
Thank you so much for this presentation for PBHL 6110.